Previous lesson, we looked at how molecules can interact with each other or attract each other. So, for example, if we have this molecule here, NH3, ammonia, we know that to hold a group of ammonia molecules together, that there would be some type of attraction between this ammonia molecule, this group of atoms here, and that it would somehow attract or have some kind of interaction with a neighboring ammonia molecule. So if you have a group of ammonia, that means you're going to have quite a few of these molecules, and there's going to be some kind of attraction or interaction between them, which this is what decides the melting and boiling points. So if you wanted to melt or boil a substance, that would mean you would have to weaken these forces of attraction to allow the molecules to move apart from each other and spread apart. Because if you want to turn something into a gas, particles have to be free to move around, and that means that they can't be held together by any force of attraction. So that there, just going to quickly, get back to no circles. Yeah. So a quick reminder that the attraction between molecules, the word for this is an meaning between, intermolecular, in between molecules, force of attraction, intermolecular force of attraction. We learned so far that there were two types that we've looked at: van der Waals forces, which are the weakest type of force. And again, if you want to see how those are created, go and watch the video on van der Waals forces. And then we watched the second video, which talked about dipole-dipole forces. A stronger type of force than van der Waals, and they arise due to the formation of dipoles in polar molecules. So say, for example, this one here, this is HCl. In this case, the chlorine is much more electronegative than the hydrogen. And what happens here is that the chlorine gets a delta or partial negative charge, and hydrogen gets a partial positive charge. Again, if this makes no sense, I advise you to go watch that video before you watch this one. What are dipole-dipole interactions or dipole-dipole forces of attraction? And because this is a delta negative, that means that there will be an attraction for any neighboring HCl molecule that passes close by. So for example, here's the hydrogen of another HCl molecule. And because the hydrogen is delta positive, well, we know about what happens: charges, opposites attract. So these two things will have a slight attraction. Now, it's not going to be a really strong attraction that holds them rigid, stuck together. This is kind of just like, as they pass each other, they just grab hands for a second, if you like, think of it like that. And the stronger they grab hands for that second, the stronger the intermolecular forces are. So this here was an example of a dipole force of attraction. And it exists where you have molecules that have permanent dipoles like this, polar molecules. Polar molecules. What we're going to look at today is a special case of dipole forces, where sometimes they can be just a little bit stronger. And this substance here, ammonia, is a good example of this. So I'm going to start by looking at this for a second. And ammonia has hydrogen atoms and bonded to nitrogen atoms. And again, there's electronegativity difference here. So that makes the ammonia delta minus, and each of the hydrogens is delta plus. So these will attract to another molecule by dipole-dipole interactions again, because each of the hydrogens in this second molecule are delta positive, and they're attracted to the delta minus negative nitrogen on the other molecule, and so forth. So you put more of these together, there'll be more and more of these. But there's a case where if you've got a delta positive hydrogen, so a delta positive hydrogen, if you've got one of these, delta positive hydrogen, and it's attracting to a very small electronegative atom in another molecule. So it's got to do with two things. It has to be an electronegative atom, so it has to have a delta minus charge, and it has to be a very small atom. So if you have a delta positive hydrogen attracted to a delta negative atom, which is a small atom, very small in size, the dipole-dipole forces in this case are particularly strong. Okay, now it always involves hydrogen, and it always involves a delta negative small atom. The small atoms that we're talking about are the smallest atoms on the periodic table: nitrogen, oxygen, and fluorine. Nitrogen, oxygen, and fluorine. These are the smallest and most electronegative atoms on the periodic table. So if you have a delta positive hydrogen intermolecular forcing or dipole-dipole interacting with one of these atoms, an N, an O, or an F, you have a very an increased strength type of dipole-dipole force. So you see here in this case, we have this. We have a delta negative nitrogen, and nitrogen is a small atom, and it's in this dipole-dipole bonded to a hydrogen atom, which is delta positive. So this is one of these special cases. We call this particular type of dipole-dipole interaction, we call it a hydrogen bond. So the clue in the word here is it's a hydrogen bond or a hydrogen. Yeah, I don't like the word bond here because it makes you think, I always think the bond is this line, this solid line, and it's not one of those. So I don't really like the word bond here, but unfortunately we're stuck with it. It's just what they're called. It is an intermolecular force. It's this force of attraction here. And it's called a hydrogen bond because it always has to involve a hydrogen. So you always have to have a delta positive hydrogen, just like we have here. This is a delta positive hydrogen, and it's dipole-dipole attraction to a small delta negative atom, small partial negative atom, which is nitrogen. So this here is what we call hydrogen bonding. So this is stronger than dipole-dipole forces or van der Waals forces. So this is technically the strongest type of intermolecular force. So the effect that this is going to have on boiling points and melting points is these types of molecules are going to have slightly higher melting and boiling points than molecules with dipole-dipole forces or with just van der Waals forces. So they're a little bit increased strength. Another example of a molecule that does this, and this is a really important one actually, is water. Water is H2O, like this. And what happens here is that the hydrogen is a delta negative atom, delta 2 negative, because it's taken the share of electrons from both of these bonds, and each of these is a delta positive atom, like that. If you bring another water molecule close, again, this oxygen is delta 2 minus, and this hydrogen are delta positive, like that. Well, there is a dipole-dipole interaction between the hydrogen of one molecule and the oxygen of another molecule. And again, this is a delta positive H interacting with a delta negative oxygen atom. And oxygen was one of the small electronegative atoms that we needed up here. Remember what we said here? Here it is. Okay, sorry, this isn't right in front of me here now, just at the second. Yeah, here. Oxygen was one of them. So in this case, this is hydrogen bonding that occurs between water molecules. So again, that's slightly increased strength type of dipole-dipole interactions. Right, so what we're going to do is we're going to fill out this table here. Okay, so why do they arise? So the first thing that I want you to do is pause the video. You can take down the title, Why Do They Arise? And see, can you draw the diagram for hydrogen bonding in water? Pause the video, do that now. Okay, so the first thing that you should have done here is you should have had a water molecule drawn like this. You have a delta 2 minus charge on the oxygen, and you have a delta, oh, sorry, that's not a delta sign, sorry. You have a delta positive on each of the hydrogens. This is a polar molecule because the centers of charge are separated. So again, if you're not sure what that means, trying to find out if a molecule is polar or non-polar, go and watch that video, okay? But the center of negative charge is at that end of the molecule where the oxygen is, and the center of positive charge is down at this end where the hydrogens are. So they're in different places. So we've got two opposite ends of the molecule, if you like to think of it. So this end will be the negative end, and this end will be the positive end. Okay, so hopefully that makes sense. So this is a polar molecule, so that's important. Has to be a polar molecule in this case if we're going to have hydrogen bonding. Okay, and of course, if you bring another water molecule close, well, it's identical to this one. It's got a delta 2 minus charge on the oxygen and a delta positive here, and there's an interaction between the hydrogen on one water molecule and the oxygen on another. So this here is what we call a hydrogen bond. Okay, so why do they arise in words? Okay, so looking at that diagram can explain how hydrogen bonds form. Pause the video and have a go at that now. Okay, so first of all, I would say it's a special case of dipole-dipole interaction. If you didn't put that, okay, what does it need? It needs a delta negative delta positive hydrogen atom. And it interacts with something. Pause the video and finish it off. What does it have to interact with? Interacts with a small delta negative atom. Example, what are the 3 atoms that we're talking about? So in this box here, what do we mean by small? Which ones does it have to be? Pause the video, write them down. All right, the ones we're interested in here are nitrogen, oxygen, and fluorine. Okay, so the top right-hand side of the periodic table, the smallest and most electronegative atoms. If you look at those, they've got the smallest radius and they've got the highest electronegativities. All right, next one. What intermolecular forces are also always present? Okay, so pause the video, write that down. Okay, so definitely van der Waals forces. So every molecule with electrons moving inside is going to have van der Waals forces. They're always present. I wouldn't say they've also got dipole-dipole forces because this is their dipole-dipole force. It's just a bit stronger than a standard one. Okay, so comparison to van der Waals forces or permanent dipole. Are they stronger or weaker? So permanent dipole is just dipole-dipole forces. Is this hydrogen bond stronger or weaker than them? Pause the video, write down the answer. Okay, so what you should have said here is they are stronger than both. If we were to make a list here, it would say van der Waals are less than or weaker than dipole-dipole. And these are weaker than hydrogen bonding. Hydrogen are the strongest. Effect on physical properties. Pause the video. What's this going to mean for melting and boiling points? Okay, so effect on physical properties, they will have slightly higher melting points and boiling points. This might not seem significant, but it actually is very significant. The size of the water molecule, H2O, is quite a small molecule. If hydrogen bonding didn't exist, if it wasn't a special thing, and it was just dipole-dipole force, the same as other molecules, well then water, believe it or not, would be a gas at room temperature. It would be steam. And that would be pretty useless for humans, because humans rely on liquid water really, obviously we know that we need to drink up to 3.5 to 4 liters a day. You have to do that to stay healthy, to stay alive. So if water was a gas at room temperature, which is the temperature that we live our lives at, then we wouldn't have water, liquid water to drink. So obviously that would be a massive problem. So it's critical to life on Earth, the fact that hydrogen bonding exists and that water is a liquid at room temperature. Okay, so here's a really important fact for us, I suppose. Right, here's a little set of questions around that now. Pause the video. I want you to pause the video and I want you to try questions 169 to 172. Okay, we've gone through 2 molecules that can undergo hydrogen bonding. We've already looked at 2 examples of that. That should be pretty straightforward. And I think you guys should be able to work out the rest. Just be careful here when it says state the number of electrons in methane. It's the whole molecule. So you got to work out how many electrons are in each of the atoms and then add them up. Okay, so again, pretty sure you should be able to do the rest of them. Okay, all right, so we'll see you the next day in class and we'll go through these answers. Oh, quick reminder, guys, if any of you have any other topic or if there's something missed in class that you want me to make a video about, just stick a comment down below so I'll know what ones you want me to do. So if there's something that's still bothering you, that you're still confused on a topic, even if it's from a while ago, go ahead, stick in a comment down below this video and then I'll go ahead and make that for you after.